Welcome everyone for this Thursday session. Good morning. So today we'll start with a pedagogical by Alvise Bastianello from CNRS, Cergy, Paris Dauphine University.
That's perfect. Thank you very much.
Yes, and he's going to talk about Soliton gases. So
thank you very much for having me here. It's great. Is it on? Yeah, but maybe it's too far. How about now? Good?
Yeah.
I think so. Okay. Well, thank you very much for having me here. I know that it's still early morning, so I'm going to try to be as light as possible, as entertaining as possible, but I want to convey actually some interesting story. First of all, this will be essentially a pedagogical lecture on classical topics, but with a quantum kick. I'm not a classical guy myself. I've been like forming the quantum integrability, but I found myself at the beginning a bit by mistake. I started doing classical integrability as well, and then I found out that there is quite a lot to be said there. Okay. So what are Soliton gases? The idea is quite simple. Okay. We would like to study a system of partial differential equations, some field theory, classical field theory, plus some random initial condition. This means that I'm not really interested in fine details and exact solution, but actually on the emergent large-scale properties. Of this, I would like to develop a statistical mechanical description that can be articulated in two different things: doing thermodynamics, a la Gibbs ensemble, or maybe something more general, and of course also hydrodynamics. I want to keep these two separated because as you're gonna say, I see in the story, these started as separate topics actually. This altogether, this program in integral PDEs, that will be eventually my focus, is called Soliton gases, but there are two versions of that. So I came prepared because to make this figure took me a bit, but I want you to appreciate what's going on here, okay? This is a timeline that starts very back in the past, around 1970, let's say. I draw three lines. The first one is quantum integrability. We're going to need it. You are quite familiar with that, especially after this conference, I would say. Then there is the statistical mechanics of Soliton gases. Here we are classical. We ask about a question about thermodynamics. And then there is the kinetic picture of Soliton gases that has something to do with hydrodynamics. Okay? Is, I would say, almost equivalent, but that almost is important. What is the story in the quantum case? Well, the quantum case starts back, well, apart from the first papers about the exact solution or quantum interval model, let's say it starts in 1969 with Yang that develops a thermodynamic approach to interval models, to quantum interval model, okay? It's what we call TBA. Then, of course, a lot of interesting developments, but I just want to highlight the milestone. 2007, it came Marcos with the idea of the GG. Actually, learned that the paper is from 2006 now, published 2007, but that's good. A lot of people studied that, but let me say that this is a milestone that said that moved thermodynamics from standard equilibrium to non-equilibrium situations, but still things were homogeneous, kind of static. Another breakthrough, 2016, is Generalized Hydrodynamics. I'm just citing the first two papers. Most actually of the developers are here in the audience, and of course a lot of different developments, okay? But I just want to focus on the first one. This is the quantum integrability, so you have to gather a smooth flow from thermodynamics all the way to generalization of thermodynamics to non-equilibrium and to hydrodynamics. What does it happen instead on the classical side of the story? Well, from the point of view of statistical mechanics, it started in 1975, where they developed first an approximate idea and hinted that could be used exactly in interval systems. Here in 1984, there's been the first proposal of a sort of TBA-like description, but for classical Soliton gases. It was an ansatz. And then in 1990, okay, but here there are a lot of papers, I'm just citing the milestone. In 1990, Chung showed that this ansatz, it is not correct. So in practice, the Soliton gas statistical mechanics approach to thermodynamics could not work because it didn't match with limiting known cases. Okay, we're gonna go back to that later. In parallel, and I want to stress completely parallel without mention to StatMech, have been developed a kinetic approach to Soliton gases. Okay, you don't ask about thermodynamics, but you ask how things are moving. It started back in 1971 with Zakharov, that developed the picture of a Soliton gas moving in a dilute gas of solitons, still with some approximations. A lot of studies, but then there is a breakthrough in 2003 by Gennady L about dense Soliton gases. Okay, not only one soliton in a background of smaller solitons, but really at the dense case. After, another important milestone is integrable turbulence introduced by Zakharov in 2009. I'm going to explain what these terms are, okay, and further developments. Now, it turns out that dense Soliton gas is actually very much connected to generalized hydrodynamics. Actually, they are almost equivalent. And the GGE is very connected to integrable turbulence. Okay? Actually, for understand this connection, we should thank nice paper by Benjamin, Thibault, and Gennady that established really the dictionary between one method and the other one on the KdV Soliton gas. Okay, establishing like a dictionary. However, this connection is true, but let me put it like this. In certain aspects, the quantum story is more developed because I have together statistical mechanics and the kinetic picture that makes to hydrodynamics. This case here, instead, dense Soliton gas is a kinetic picture of Soliton gas that doesn't know about fluctuations because you don't have stat mech, because here was blocked. Integrable turbulence is the idea that if you let a system integrable PD to evolve homogeneous in space, at a certain point we reach a stationary state that is indeed a GG, but does not be called like that. Actually, in this paper, there is the expression, the GG, the same as Marcos wrote in 2007. I think that is quite fun, interesting how the two concepts are swapped in time in the timeline. Okay, but now you see that this program is not completely fulfilled, like it's not developed as in the quantum case. And today's talk is about doing that and try to understand why this guy doesn't work, okay? And how to solve it in particular. So for this, I need to add some further reference to the list that are here. Is an interesting paper for 2009 by De Luca and Musardo, from 2014, sorry, where they have this idea. Let's look at a quantum integral model and let's try to do the semi-classical limit of that to study a classical integral model. It has been done in the Sinch-Gordon model that is, I would say, a still fairly nice model, but again, is an interesting concept. Then here, let's say that we are in 2018. I did with, sorry not writing the whole name, but just mentioned with Takato, Jerome, and Benjamin and J.R. Watts, we look at semi-classical limit of GHD. So now we are connecting this. Okay. And what is important that we can extend this whole machinery to systematically attack the problem of Soliton gases that before has been still unsolved. What you're going to do in this way, you're going to first of all fix thermodynamics. This actually happened a bit later, let's say like this, in 2022, for the nonlinear Schrödinger was. You can still start developing systematically from the knowledge of quantum integrable model the dynamics of classical integrable system, fusing together statistical mechanics and kinetic picture, just because you have the methodology of the quantum case. And as you see, this in the end solved a problem that is, well, solved a problem to some extent that have been open for about 30 years. So, yeah. Yeah, sorry?
You know, just a small addition to the history. I mean, there's the group of Mertens, this is mid-80s, 1980. He looked at semi-classical limit for the total lattice, right? And you know, this sort of didn't continue really, but I mean, it's also one of these historic points.
I have some further reference later, okay? I'm focusing mostly on what this guy started, so not on Toda, but on Saint-Gord, but my feeling is that Toda could be a bit simpler, okay? But this I do not, I'm not an expert on Toda. But for sine Gordon, I'm not the first that tried to the semi-classical limit. Here is nonlinear Schrödinger, but later we did also sine Gordon. Already this guy here tried, and a bunch of other people that you're gonna see reference later, but how can I say it in a polite manner? They got it wrong, okay? They forgot, they didn't do correctly on sine Gordon. And in sine Gordon is quite, how say, non-trivial what's happening, okay? We're gonna see later. But of course, semi-classical limit is not completely new, it started also here. And thank you very much for the addition. I was not familiar with that paper. Okay, so let's go to the program. What I want to do today. So we're going to start with an introduction to Soliton gases. I don't want to use here integrability. It will be an approximate hand-down introduction. Then I'm going to try to go integrable. We start mech of PDEs. Then I want to cover the kinetic picture to Soliton gases. Semi-classical limit of quantum integrability to fix the problem. This fixes this. And if time permits, I want also to mention that these are completely theoretical development, but there is an analogous development also for experiments. So I know this is pretty ambitious because like in the end there are 50 years of physics in now less than 2 hours. Let's see how do we go. But I develop in a modular way that the worst case scenario I'm gonna just cut out one of these, telling you what the story is, and the talk should still work. Of course, this depends also on how many questions you have and how we are doing with time, all right? If you have any question, please interrupt me. So let's start with the introduction to certain gases. What do I want to do? I want to study stat mech, or if you want, thermodynamics. I want to be classical, and in general, imagine that I have some field theory of which I want to compute a partition function. I'm going to do a Laplace integral. It's an Hamiltonian. This function of a field and the conjugate variables. Okay, for me, phi is the reference field and p is the conjugate variable. If you want a concrete example, you can imagine something like this. With B some potential. Okay. Notice that I'm not now focusing integrability. I want just to try to say something about this general problem. Now, of course, since this guy here is interacting, this is a very hard problem. In general, we do not know how to solve it exactly in full generality. Okay, but let me try to start doing something approximate. Imagine that I'm choosing some maybe complicated potential for the interaction that looks like this. Now, in general, no hope to solve it. It's fully nonlinear, it's very difficult. However, if we are at very low temperatures, we can, of course, start introducing harmonic approximation of the potential. So the idea is to replace this guy with the proper harmonic approximation. And now, once we are harmonic, we know how to solve it. Okay? How do we solve it? Well, we want to find the modes that are going to analyze this Hamiltonian. In this case, you can just sit down. Of course, you want to have like a canonical transformation between the variable phi and p to the right guys. You're going to find out that this is the transformation that they're looking for. Where A is my new canonical variable. In terms of these guys, the Hamiltonian is really diagonalized. With the energy being relativistic form. Okay? Easy like this. Now, of course, we know how to solve the path integral because we can just change variables. The transformation is canonical. We don't get any Jacobian. And the Hamiltonian will be quadratic and the kappa over different modes. Yes?
I'm slightly confused. I mean, are you considering one spatial dimensional system? Or?
Yeah, sorry, like I should have said that because in the end I want to go to intervals BDs. So I'm starting not with integrability, but I want to go there. So it will be one spatial dimension. You can also generalize it, this approximation, to many dimensions.
Just to make sure, I mean, the thermodynamics that I know is that in Euclidean space.
Sorry, say it again?
The thermodynamics I know is that you have Euclidean space. And,
this is classical. You don't have the Euclidean space. You just have beta in front of that.
Yeah, I know, but why do you have time in it?
There's no time here. This is statistical mechanics. I'm not doing auto equilibrium, not involving anything.
Okay, good. Thank you. So what is P again? P
is the conjugate variable. You have some Poisson bracket, your X. I always misplace like which one is goes, but this is like delta X of Y. These are Poisson brackets. In quantum mechanics, this would be a commutator. In the classical case, are Poisson brackets.
I understand, probably difference in language, but P is usually in free field theory. Isn't P like partial T of phi? I'm confused.
Yeah, but here I'm doing thermodynamics, so I don't have dt. Of course, if I write down the PD, P is dt of phi. But in principle, they are two different variables. It's as when you solve the harmonic oscillator, you have P square plus Q square. And this would be just a classical harmonic oscillator. And of course, in this case, you get that P dot, the P is Q dot, and Q dot is equal minus, is it correct? No, sorry, Q dot is P, and P dot is minus Q.
Okay, I'm probably fine. Okay, thank you.
Yeah? Because you need it for having like, actually I forgot a factorial. You need it for making the transformation canonical, because you can just absorb this in the definition of K, but AK will not obey canonical Poisson brackets. If you're not canonical, you should take into account the Jacobi and the change of variable. And of course, this is annoying. So it's better to find a canonical transformation. Okay. So this mode diagonalizes the Hamiltonian. And notice that these are just plane waves. Okay. So this mode here is actually describing something that we're going to find also later, and we call radiative modes or radiation. Okay. For me, radiation is a mode, in this case is linear. In more complicated case can be also nonlinear, that diagonalizes the Hamiltonian, and it is not localized in space, it's dispersive. Okay? But now I promise you statistical mechanics, so I want to understand what is statistical mechanics or radiative modes. How do we do that? Well, you just plug this definition, the path integral, you do the transformation. What we're going to find is essentially this. Canonical transformation. So this is the guy I want to solve. But now, of course, I can solve it as Gaussian, but actually you're going to learn more if you don't try to solve it exactly, but you do something different. Okay? And for doing something different, I mean that I want to do another change of variable. It is the following. I want to describe AK as some modulus that I will call rho k and a phase. We go right. Now you see that when I transform this with this change of variable, this guy here will just be something like this, where rho of k is giving now really the density to the modes that have a certain energy. Here I have another variable that is just an angle that I don't care, I want to integrate over. Okay? But here there is also a square root. It means that you have a non-trivial Jacobian. And if you, well, we can just, you have an anterior Jacobian, and why didn't I write it here? If you plug in the path integral, the non-trivial Jacobian, what you're gonna get is that integrating the angle, you're gonna find out this change in path integral. Of course, you have to be a bit careful. The 2 pi's are coming from essentially the integration of the phase, and this is coming from the fact that you get essentially a 1 over factor rho coming out of the Jacobian. Now, why do we like this? Because now this is in the form of free energy. This, if you want, a free energy. In the limit of large system size, the path integral localizes on the saddle point of the free energy. So now you recover thermodynamics because you just have to minimize this free energy. Here we get the energy of the mode, and here we get the entropy of the mode. Okay? Because I'm just using that free energy I can define this way. So here we're learning what is the entropy of radiation. So relative modes will be the localized modes with Rayleigh-Jeans entropy. I'm calling Rayleigh-Jeans, maybe you don't recognize directly from the entropy, but if you minimize this free energy, what you're gonna find is that OK, on average expectation value on this that will be actually fixed by the saddle point, is just 1 over beta, the energy of the mode. That is the distribution of classical waves that is Rayleigh-Jeans distribution. Okay, so here we have a mode not localized and Rayleigh-Jeans. If you have questions, please let me know. Yeah.
The entropy that you wrote doesn't have the usual yang-yang form. Is it just because you didn't write like that, or it's impossible to?
So is it again, doesn't?
The entropy that you wrote it doesn't have the usual yang-yang form, right?
Well, like it is still entropy. It looks like yang-yang form in the sense that it's the integral over the modes of some quantity. But that quantity, since we are not quantum, is different. Indeed.
Okay. Yeah.
Okay. If you would have, instead of a classical system, I promote a field to be quantum, you can do the same, but now this will be bosonic modes, and the entropy you're going to get here is of Bose-Einstein type. But we are classical, and we get radiation.
This one, so you still have the beta in the exponent or not?
Yes, yes. It should be there. If it's not there, it's a typo. Yes, we have it. Yeah, of course, sorry. It could be that I make typo here and there, but the end equation should be correct. Thank you for spotting it. Right? Now, we found radiative modes. Now they're quite simple. It's just a harmonic oscillator. But maybe it's not the only problem that we want to look at. We could have different potential that have a different form. Imagine now that instead of a single minimum, we have 2. Okay? Now, my artistic skills would like to put these 2 guys here at the same level. In terms of energy, I can be on one side or I can be in the other one. If I do a low temperature approximation, I can really decide on which one I am. Okay? What can I do? Well, of course, I can just consider again an harmonic approximation here. I'm going to find that the small fluctuations here are of radiative type. I can do the same here. But I'm gonna miss something because if I just consider radiation, I'm gonna be doomed to be either here or there. But we know that in one dimension, order is killed by thermal fluctuation. So I need to do something more. What I need is to consider an excitation that is able to bring me from one bottom of the well to the other one. This is what a soliton does. A soliton, actually for this potential, you can find always the profile of the soliton exactly. Soliton is just a profile of the field that looks like this. You want here would be minus phi 0, phi 0. This guy is going from minus phi 0 to phi 0, is interpolating between the two well. It exists static, but since we are a relativistic invariant, in this case, you can also move it at arbitrary momentum with relativistic and dispersion law. So this we had dispersion law of this form where the mass, capital M, depends on the model. Now, if you think about what we expect statistical mechanics to be in this case, you're going to have typically a profile like this. We have solitons, but we have also topological soliton, but we also have the other way around because we can also go from this well to the other one. And so a typical profile will look like this with fluctuation on top of that. And the idea now is that I can describe the thermodynamics as a dilute gas of solitons embedded in a gas radiation. So in this case, I'm going to add that partition function factorized in radiation and solitons. Where solitons, I can consider them as particle-like excitations. Yes?
I mean, here, this is the exact one soliton solution, right? But it's not a soliton in the sense of integrable system that they have factorized scatter.
I don't have integrability in the game yet, okay? I am not using that yet, okay? So here is, everything is approximate, but it's hand down what like smart physics would do in this case, yes. Essentially, the idea is this, because if you have a very low density radiation, okay, low density radiation, we are low temperature, you're gonna have a soliton every 1,000 kilometers. You have a lot of radiation here, but the points where the radiation and the soliton meet is so negligible, and the amplitude of the radiation is so negligible that you can forget interactions. Of course, if you want to be more precise, you can start doing perturbation theory. There are beautiful books doing that. It's super complicated, but we will not need it because instead of doing that, we're going to jump to integrability. And that, in that case, we're going to solve the problem exactly. Okay? So I'm going to treat the solitons as if they were like standard particles. Of course, they're not distinguishable. We're going to put a Boltzmann term. Then what I want to do is to integrate over the position of the solitons, integrate over the momenta, and treat the solitons as a gas of particles with certain momenta. Okay? If the solitons are very far from each other, I can just factorize the energy. Now, again, this starts to be a bit complicated. You can factorize the integrals, you could try to do it, but it's not the smartest way to do so. Okay, what we want to do now is to introduce a counting function for the density of solitons. I want to introduce again a rho, like before for radiation. I put an S that to remember myself that it is a soliton, that is the, let's say L times dk is the number of solitons with a momentum in an interval, in a small interval. This is small d. Okay. Now, when I do so, I'm taking my momentum space, I'm chopping it in cells, and I start to count the solitons belonging to one cell and another one. When I do so, yeah?
Excitation.
the mass of the solid depends on interactions, okay? And you can compute it. There are ways to compute it. For the time being, it is model dependent, it's just a parameter, okay? Just imagine that we know it. Yeah? Yes?
So when you write this path integral, there should be some long distance cutoff or something like that, which says that it's a dilute gas, in the sense that compared to the width of the kink, they are sufficiently well separated.
This is a self-consistent approximation in the sense that if I go low temperature, the density of the soliton is lowered as well. So if you want, we're using the temperature as the cutoff in terms of the, because like this guy here have a finite energy. So the gap exponential minus beta energy is different from radiation, okay? But of course, we are working here in a scenario dilute gas. And yeah, that is approximation we're doing.
Thank you.
Okay. Now, if I want to compute a partition function, I need to keep into account that I have a different way of arranging solitons in each cell. So I get some combinatory factor. And the way, if I fix of K, then I have, after you do some combinatorics, this is supposed to be a factorial, and this is a factorial as well. For a fixer, this is the number of modes or arrangement that you can have, okay? So of course, we need to keep into account when we want to write a partition function with this guy. I will cut it short. What you have to do here is just assume that in each cell, there is a large number of particles, start using Stirling approximation. Stirling means exponential. Exponential will go together with the energy and will give you, in the end, the entropic factor that you expect for solitons. What you get is the following. 1 minus and of course, this is the density of the solitons. Again, you have this is a free energy. This is a free energy. This the beta energy. And this we recognize to be the entropy of the solitons. This is an entropy of Maxwell-Boltzmann type. Okay, comes just out from combinatorics. See what you do when you solve for free particles in a gas. And if out of this you minimize the free energy, you're going to find out that the expectation value of the density of soliton that in the end will be fixed, because for large L you go to some the point, this guy is simply of Maxwell-Boltzmann type, classical particles. Okay, so for me, the loose definition of solitons, okay, are localized modes with Maxwell-Boltzmann type of statistics, okay? So in these field theories, we usually expect just from this low temperature calculation to have radiation and solitons that are different modes, delocalized with different statistics, Rayleigh-Jeans and Maxwell-Boltzmann. This has been an approximate picture so far, working for low temperature. Now we're going to use integrability to make it exact and try to follow this path here, crashing here and fixing it later.
Sorry, can I? So, so these solitons can be created or destroyed as well, because
we are non-integrable now. In any case, we're considering just thermal fluctuation, so there's no dynamics. Here, you do not really know too much if you're integrable or not.
So, but you don't have a chemical potential for the integral of rho there?
I choose a model where it is not natural to have a chemical potential, because I'm looking at the Hamiltonian that now I erased, a 5 to the 4. You could have, for example, another system like a nonlinear Schrodinger, where you also have a chemical potential, but I want just to have like the simple partition function. In the integral case, actually, the partition function itself is useful, but up to a certain point, we're going to introduce Generalized Gibbs Ensemble in this setup. So we're going to have a lot of chemical potential. And you can choose your favorite.
Thanks a lot.
Right? Yes? So that would be a gas of particles, okay? And well, of course, you can do statistical mechanics of a gas of particles, okay? What I want to show here is that even though we have a PDE, that is a differential equation, we can find some excitations that look like particle. So we use a particle-like thermodynamics to study a continuous field theory, continuous classical field theory. Okay, then, so you want a gas of particles with some repulsive potential between them. Well, yes, you can start doing statistical mechanics, and if particles have a low temperature, zero energy situation where like they're arranged on a certain lattice, you can start doing small perturbation around that and write down harmonic approximation. But there you start with particles, not that they emerge from the interaction, you start with particles. Okay. I will make more room. Actually, I can get rid of everything, but please, if there are questions, let me know. I should stress, because now we're going to find them, that I introduced solitons like topological objects, okay? Because I introduced them as kinks. But they could also be solitons that are not topological, in the sense that the limit far to the left and far to the right of the function is the same, but yet there are localized modes, and you can build the same kind of approximation. I just choose to introduce them in a topological way because they're easier to justify, to visualize. Otherwise, you should get your hand dirty with the calculations. Yeah, sorry, let me write it again, because now we're going to use it. So this is the Hamiltonian that in the end is going to result in a PDE that is of this type, minus this the derivative of potential, the field. Okay, cool. Yeah. Let me formulate. You want the object to be local from the point of view of energy, because when you do thermodynamics, you see the energy. The topological Soliton I show has a different field, but is interpolated between two vacua. So right and left, the energy goes to 0. If you look at the energy profile carried by the Soliton, that is well localized. Okay. From the point of view of correlation functions, because for correlation function of the field that for which the Soliton is topological, you're going to have very nice properties. For example, if I put the fields here and there, I put a non-topological Soliton in between, nothing will change. As soon as I put one topological Soliton, they will change. That is why order in one dimension is not stable for time fluctuations, because as far as they are, I always have at least one Soliton in between because of fluctuations, and that will destroy order. Okay. Now, sorry? Okay, sure. I want to keep up for highlighting, but let me switch. Okay, so now we want to do integrable models. So not all the PDEs are integrable, of course. You have to choose carefully your form of interaction. I would still want to keep something of this form, okay? But now I have two different choices, at least, okay? For example, I can choose this guy to be 1 minus cosine phi, okay? Or hyperbolic cosine of the field, okay? Now, I tell you that this equation here are integrable. Of course, they are not the only integrable equations, but they really connect with what we have done so far. Because in this case, the potential is periodic in phi. It means that the potential looks like this. You have a lot of different degenerate minima, and you could have topological solitons separated between one and the other one. Instead, in this case, you get a very steep potential, but with only a single well. So you're going to be a situation closer to a radiative case. Since also here you could expect in principle radiation, in the end we're going to focus on this choice here. That is the Sine-Gordon model. I'm doing that mostly because it connects with what I told you before, and also because historically this is the model that has been analyzed here. Okay, it's not the only integral equation in integral PDE. There are other interesting ones. Well, of course, we have PDB, we have TODA, we have the nonlinear Schrodinger equation, and this will come back later because it's a bit simpler for discussing the kinetic. We have the Landau-Lifshitz equation, and of course, others that I'm surely forgetting. But these for me are the more like well-known and physically relevant for the time being. If you have other examples, please correct me. Okay. So how does it work in Sine-Gordon? Sine-Gordon in general, integrable PDEs. We already had many introductions of integrability from the purely classical case, had the rods from the quantum case, and the same ideas holds also in classical PDEs. We're going to have infinitely many conservation laws. Conserve quantities in the form like this, with this being a localized operator or like a function of the field. Okay, this has very important consequences as it gives you elastic scattering and excitation. And it supports non-trivial stationary states in the forms of generalized Gibbs ensembles. So if you want, instead of having just thermodynamics with Hamiltonian, we can generalize it to other scenario where we put a lot of temperature, chemical potential associated with the charges. Okay, so we're going to directly look at thermodynamics in this form. This holds in general, but I'm going to make examples on the Sine-Gordon field theory because this is what we are going to do. Okay. What is the spectrum of Sine-Gordon? I mean, what are the excitation we're having? Of course, we're going to have topological solitons. Okay. We know the profile exactly. I can just write it down. I will refer to topological solitons as kinks because we have also other solitons that are not topological. So let me just use this notation. Kink, I hope that I didn't mess it up factor, but can be written like this. Where theta is the rapidity. Before we use the momentum, but this is a relativistic invariant model, so maybe using the rapidity is smarter. Okay, we are just changing a bit the parameterization. And of course, this guy here has energy. In terms of the rapidity, it is just the mass of the soliton cosine hyperbolic of the rapidity, and the momentum that is sine hyperbolic of the rapidity. If you change variable, you get again the same relativistic expression that we showed before. These are not the only excitation you can have, okay? Because you can also have non-topological solitons. And these are called breeders. Breeders because these are not, you can put them at rest in space, but they will keep on oscillating, okay? Plus, there is the question, and let me put this as a question mark. I'm going to comment more later. We could have radiation. Okay, we expect it from a low temperature expansion. And if you do more advanced techniques or inverse scattering, if I have time, I'm going to cover them later, you're going to see that, okay? But now let me focus on the topological soliton first, okay? Now this is an interval model. You have analytical techniques to solve exactly dynamics, at least at the low particle level, okay? So we can write down a two-king solution in this form. This is an exact calculation. The exact calculation, I want to write it down, is not really too much important, the actual form, okay? But I want to use it to show you what the dynamics of two solitons look like, okay? This is describing, you can check the asymptotics if you go back in time, is describing a soliton traveling rapidity theta and another soliton traveling rapidity theta again, okay? What you can do, you can take the back in time large limit and the forward in time large limit. And what you're gonna find is that after this, at a long time, well, the solitons will have scattered. This is minus theta, of course, minus theta. The solitons are scattered, and in this scattering, you find again exactly the same solitons with no other modes in the game. You don't see radiation, you don't see other solitons. And this is a peculiarity of interval systems that have elastic scattering. This holds for this simple scattering event, but holds in general for all the modes in interval system, both solitons and even radiative modes, okay? The scattering is not trivial, okay? Because you can see, if you plot it in X and time and just look at where you have the bump in energy profile, you're gonna see the solitons are doing this. I hope that it is clear, but it's a picture that I've seen many times in this hydrodynamics and so on, hydrodynamic lectures. What you're gonna find is that the soliton doesn't go to the same position it would have if no other soliton is present in the game, but is piling up a shift, okay? That actually depends on the rapidities of the two solitons, okay? Here we have different, opposite rapidities, but we can generalize to find rapidities. And this guy, let me parameterize like this. This you extract directly from the asymptotic solution of this guy here. You can write it down as, let's say this is for the kinks, and this of this form. Don't cross, sorry. So let me not cross it. And it is of this form. Okay. It is not very important the form, it is important that it exists. Okay, I'm gonna use it just as a function later on. Okay. Sure.
like in terms of the pictures that you draw before, like what is the difference between topological and non-topological solitons? Like, is it a pair of kink anti-kink, or it's a bit different?
The topological soliton is just, in terms of the field, a localized bump in the field.
Yes.
Both topological and non-topological solitons, if you look at the energy profile, they look like a bump. But if you look at the field profile, topological has different asymptotics, non-topological has the same asymptotics.
But if I bring two kink anti-kink together, is it like a bit non-topological? Like, how does the like?
That is a two kink solution. It's not a single soliton. I can put two topological solitons with different topological charge, and the global charge is 0 again. Okay, but these are topological solitons because they scatter and they eventually go very far from each other. You can resolve independently two kinks.
I see. Can I understand? Is there a pictorial understanding of the breathers in terms of the previous?
I'm about to do that.
Ah, okay.
Okay. So now I promise you breathers. This is now fairly obvious from like whatever we saw in this conference, but you know that you see that in this case, since you have asymptotic particles, the total energy of this configuration is just the sum of the energies of the two solitons, because I can just let them scatter, go very far apart. The total energy is sum of the energies, and this works not only for the energy, but also for the local charges, okay? Now, I promise you breathers. Okay, and breathers are of this form. They're solitons, they're not topological, and they keep oscillating. Now, it turns out that the two-kink solution I wrote before, check for FS the other side of the blackboard, in principle solves the Sangon equation for arbitrary value of the rapidity. But in general, if the rapidities are not real, the solution is unphysical. But it's an exception. What you can do here is take the rapidity and analytically continue to be purely imaginary. Okay, where sigma is another parameter that now will run from 0 to 1. What you're going to find in this case is that the profile is still physical. And what does it describe now? Describes a breather. Describes a bound states of two topological kink and anti-kink. In the two kink profile, the total energy is just the kink mass. The energy of the two kinks. Of course, theta and minus theta are the same, but once I do the analytical continuation, what you're going to find is that the new particle that now is a bound state has energy that depends on in this case it's rest energy, but you can also put it in motion. So I'm going to take, I'm going to keep a real rapidity here, say that, and the internal index, and this now has energy like this. So the energy of the breather is twice the mass of the kinks. Okay, so it is just the mass of the breather. Okay, see, the mass of the breather, m of sigma. It has twice the mass of the kinks times a factor that runs between 1 and 0. Okay, so when you have like that sigma is going to be closer to 1, this guy here starts to be 1, and the energy of the breather is the same as the kinks. What does it mean? That the breather is becoming shallower and shallower and shallower, and reduce it to an asymptotic solution of kink anti-kink. On the way around, you can have a smaller breather. Okay. All right. Yeah, sigma is a free parameter that now I can change between 0 and 1. I have a family of breathers. Each sigma tag a different breather. Each of them act like independent solitons. Okay. You can also compute the scattering shift of this guy just using the fact that we know the scattering shift soliton anti-soliton. Scattering shift of many particles is additive. You can just sum it. You can do an analytical continuation at the level of the scattering shift. You're going to find all the scattering shift between soliton, kink, and breathers of all the species. There's also breather against breather. Okay? So now we know the particle content of field theory, and we know the scattering shifts. You need to do the analytical continuation. You're going to find there that it is damped in X, but it's still oscillating in time. Okay? Yeah? Yeah? Now, the fact that, okay, what does it mean static breathers and what does it mean close to each other? Okay, of course, you could be a situation like this. That you would say it is pretty static, no? It's pretty like close to each other. The theta will go to 0, but of course there's some exponential tails. Okay, this already gives you some weak potential. Now don't remember exactly if it is attractive or repulsive. Okay, I should, but you can understand from the scattering shift. I'm not able to do it out of my mind now, but this is doable. Okay, so if this guy here infinite far apart, they don't talk to each other. They will talk a bit if they're close to each other. Okay, but if you want, this is as if in a big scattering event that should do like this, is as if I'm looking at the model at this point and start to see something. Okay, but actually you can also understand the interaction between solitons without integrability. There are really beautiful books doing that in an approximate manner. But of course here we're interval, so we care about the scattering shift. Okay. Now, this is a big question mark now, because I start the whole presentation with radiation. And so you could ask yourself where it is, how we can get it. Huh? Oh, I want to use a different one, but it's not a good choice. What about radiation? Okay. Because from like a low temperature expansion, of course, low temperature expansion works also for integrability, no? It works in general, why shouldn't it work here? So there should be some radiation, we expect that. Later, you're gonna see that from inverse scattering, you still expect this mode, okay? But so far it didn't appear in the spectrum. Well, the point is that now you could either try to introduce as an independent mode or see that actually maybe it's not that much independent, okay? I don't want to posit this as a solution now, but I want to point out of a problem that will be manifested later, okay? But this is the first hint of that. So let me consider the breather. As I told you, it's something that is kind of localized, but this oscillates in time, okay? Goes up and down, if I consider breather at rest. Of course, what I can do now is also take the breather and accelerate it and put it in motion. If you do so, you do not have only oscillation in time, but also in space. A breather that is moving looks more or less like this. This is a moving breather. But of course, these are localized excitation of very large amplitude. From the point of view of But still now we have a free parameter here. So you could wonder, what does it happen if I take a breather, I consider the small sigma limit, okay? That is associated to the amplitude of the breather, okay? The other limit is you have like two kinks, so it will be large amplitude to a large extent, but you can also decrease the amplitude and something will happen. And what you're gonna find out if you do the whole business, taking the two kink solution, do an integral continuation and boost it at finite rapidity, we're gonna find a profile of a breather of species sigma and rapidity theta, the function t of x, the leading order goes to this. In this limit, I'm fixing time and x and taking the small x sigma limit. What you find here is a plane wave of an amplitude given by sigma. Sigma with some normalization in front of that. Okay? So there is already a hint. If you take this and go to the, if you take a breather, you go to the sigma to zero limit, in certain sense, you expect to recover radiation. Now there is a question, like, are these independent modes? Yes or not, or to which extent? Which are the modes that I need to include in thermodynamics to have a complete description of the statistical mechanics of the model? Okay? And now we're gonna try to do that. So now let me put it as a question mark, because as you're gonna see, people looked mainly with St. God at the beginning, statistical mechanics with only solitons, and that was not working. So the question is, do we need also radiation? Yes, no, and this would be, I would say, part of the exciting, it would be an exciting part in the story. Okay, so now we know more or less everything in the system, at least at the Soliton level. Okay, so let me simplify the notation. I don't want to distinguish kink, anti-kink, or breathers, so I will just include overall index that is running on kinks, anti-kinks, and on the breathers. So when I do summation over I, it means summation over all the different modes, okay? If the parameter is real, it means that it's an integration, okay? Just to be general and to simplify the story, okay? So StatMech according to this line of the story, okay? Now we're gonna finally finish this and we're gonna start moving to the other topics, okay? But now we are here. Well, if I'm doing StatMech, I could have just the Hamiltonian, but let me be more general, already start thinking about GGs, okay? What is this guy here if I have a collection of solitons? Well, this I can write it down as would be maybe like this. Some of the modes, I'm also integrating over the rapidities, okay? And each mode will have will carry some charge that is labeled by J, but also by an internal index, because, for example, the energy of the different solid is different, so I need to keep track of that. This is the rapidity, okay? And this now is just I theta. And this is the density of solitons of certain species I, kink, anti-kink, or breeders, and the rapidity. For simplicity, this now becomes GI of t, okay? Is a sum we imagine that somebody gave us and want just to consider, okay? Now I want to start to do thermodynamics. For doing thermodynamics, we should keep into account interaction somehow. Interaction in this case of just scattering shifts. So I want to introduce that into the game. So the fact is that now a soliton doesn't see a volume L, but it sees an effective volume, okay, that is normalized because of the other particles to the game. This will depend on the index and on the rapidity. You can immediately understand, you can write it like this. Theta. This is the momentum, is not the density, is the momentum. Sorry, but the notation is a bit closer. I'm doing just taking the volume and removing the size of the other particle, the effective size of the other particles, okay? You see the scattering shift, that are actually these two guys together, but this depends only in the arriving solitons, I can factorize it out, and here the density of the other solitons, okay? Now, it is convenient, rather than dealing with effective volume, because the scattering shift is not the derivative scattering phase only, but there is also the momentum, okay? Is what you get from the solution that we did before was here, okay? So instead of this, let me just define what are the, in the quantum case, we call the total root density, but we can also define in the classical case simply as the effective normalization with some extra factor. This guy here just take into account the ratio between the effective volume and the actual volume in the system. Okay? And so far, this is, I would say, pretty well defined. And now we want to build thermodynamics. Okay? So we know that we need to include the effective length in this case, and but we need also to include a proper entropy. And in the classical case, this is not really well known. Like, it's not rigorously known, I would say, it's an ansatz. I'll be here because I want to be close to that.
Just one question.
Yeah.
So, as against the double well potential in case of the Sine-Gordon theory,
yeah,
the multi-soliton solutions are exact, isn't that right?
Yeah. Or like you can write down multi-soliton solution for topological solid and non-topological solitons,
right?
And they're exact.
Yeah, they're exact. So, in particular, you can also go to the dense limit because they're exact.
In principle, yes, this is what the machine wants to do. If you are dilute, you forget about the disnormalization. Okay, right. But the fact that you can write down the exact solution, but you want to do thermodynamics, so you need to sum over different configurations, and this, even if you have the inverse scattering, is difficult. I will try to say more later. Okay, I hope that I can cover. If I cannot, let's discuss later. Okay, the fact that you need a phenomenological approach like this, you hope to build an exact approach, because just solving the path integral, even though it's integrable, you cannot do it right from scratch. It's a difficult problem.
So so there is an independent development of the duality between Sine-Gordon theory and the massive Thering model by Coleman and Mandal. So there was a discussion entirely in terms of the fermions.
In the quantum case, this one is classical.
Yeah, I know.
Yeah. This but yeah, that is true. Please,
so there, I mean, you know, you have either a description in terms of the original five, yeah, like the radiations, or in terms of the fermions. So it would be overcomplete to count both of them. And these fermions in the quantum theory, these fermions had the interpretation of being solitons.
The fact that in the quantum case, this machine now that I'm trying to introduce as a suggestive picture, you can make it, well, I do not know how much rigorous, but surely exact. Okay, so this you can build out of is thermodynamic better answers introduced by Young 69. You know the exact solution on the level wave function. In that case, it is easier to sum on the modes. Okay, because what we did for radiation, we identify the modes and we convert the sum from the field to the modes, and we knew how to do that. In thermal cases, nonlinear is more difficult. In the quantum case, we know because there is a mapping between the modes and a set of integers on which we have to sum over. The classical level, this mapping will be between the field and the inverse scattering solution that I will show you later. but it is not clear how to sum over that modes. Okay, so you have to be a bit, you have to make a leap of faith and hope that nothing goes wrong, but it does. Okay? The size of the system. I want to do thermodynamics, so I need to be finite size, finite density, and of course the large limit. Imagine that you can choose the boundaries. Imagine you do periodic boundary condition, or you do hard walls. From the point of view of thermodynamics, it doesn't really matter because they just change the system, the boundaries, but the bulk, the extensive part is not affected. The number, yes, the density should be fixed, no? That's the hope. Okay. But actually, that is an important question I will answer later because boundary conditions, they do not seem important. They will be, but to understand it, we need to get back to that later. Okay. Yeah. There is the hope it is exact. Okay. Let me put it like this. This is what people start developing here. Let's say, well, we have thermological Soliton gas approach on the non-integral case, and they suggest that maybe in integral case we know what the Solitons are. We can do the same game. And then people started doing that. They did what I'm about to do, hoping to get it exact, and it was not in certain cases. Okay, and we need to understand which are the problems and how we solve them. This will be part of the rest of the presentation. Yes?
And then you can basically think about moving it back in time. And then this introduces a non-trivial Jacobian matrix, which essentially gives you this kind of scattering when you resum.
Now we know what the modes are, we know the energy. In principle, we know how to sum all the modes, but to complete thermodynamics, we need to understand what entropy is. And in this case, it's non-trivial to understand what it is from scratch, okay? So here, there is an ansatz. Okay? What you do, you just assume it is Soliton-like with renormalized length. Each Soliton sees a different length, but the entropy should be the same. This is an ansatz, okay? I want to stress it. So this is for Solitons, and if you imagine in your system, there is also radiation as independent mode, you will try to do the same, okay? So in general, the entropy, you can write it if you put together, like you go to the entropy that we wrote at the beginning, you put the right factor L, you promote that to be L effective, and instead of using L effective, you use the total density of state, the total density, because it's nicer in terms of the formulation, okay? If you do so, in general, you expect you can write some of the modes. The entropy like this. Let me use this one to be the capital, and this is the contribution of each mode. That depends on the ratio between these two guys, okay? Now we write this function. This is the total density of state, okay? And you can understand that it has to be in front of that because this was P. There is just a Jacobian that is changing variables from the momentum to the rapidity. The summation should be in the low density limit flat on the momentum, but it's not in the rapidity. So there is a prefactor with the Jacobian taking care of that. And plus a normalization of things. Okay? And then you define this to be just a variable x, but this is the, let's say, and this you assume it to be of solitonic mode, okay? That it means if I remember correctly, my notes are correct, you assume it to be of this form, where I just define the relative occupancy of the mode as the ratio between the density and the total density of modes that I defined before, okay? This is for solitons. Radiation, the same thing, but with the radiative entropy that we had written before. And this is an ansatz, okay? After you do that, you can play the whole business of having like the free energy. You want to minimize it. It's a bit more difficult than before because now the equations are more complicated and non-linear, but you can find a non-linear equation. In the quantum case, called like a thermodynamic Bethe-Ansatz equation that fixes the state once you know the Lagrange multiplier of the GG. Okay, if it is thermal, it's just a temperature. You can imagine solving that. Yes? No. No, indeed, like in the 1990, they weren't really using GGs, so they just check on the thermal case. And they use sine Godot instead of non-linear Schrödinger because in sine Godot, thermal states are well defined. They check it, and it was not working. This is exactly what I'm going to write down.
Not even at infinite temperature.
Actually, infinite temperature, you have a problem because it's a field theory. Infinite temperature in the field theory is not well defined. You should go on a lattice. Okay. What you can check is low temperature. Okay. Okay. And indeed, that didn't work. So let me give you a bit of storyline. 1980, we et al. First mention of Soliton gas for St. Gautam. Okay, the first paper I mentioned is phenomenological Soliton gas on non-interval theory. Here they do more, and they say, well, maybe what we are doing could be exact for St. Gautam. Then there have been like, this is a long name that I'm gonna Jacopo, okay? I still have nightmare about writing down this name. I'm writing only the first name, but actually there are collaboration, okay? 96, then Chen, another people in, again, 86. And all these people try to approach this problem with slightly different methods, slightly different results, and keep in mind that back then it wasn't cheaper to do simulations, okay? So the way in which you check what you are doing is trying to go to limits that you can control, okay? All this guy writes some equation for the Soliton gas. In the end, the outcome was always the same, slightly different method, but the outcome was always the same. There was a debate, it works, it doesn't work. If you check this paper, they claim to have exact solutions. Then there is a very nice paper by Schwung in 1990, okay? This method here are just solitons without radiation, okay? And here, this guy took all the methods that have been there before, they make a comparison and show that all of them are not correct. Just checking the low temperature regime. Okay? It's a bit sad story, isn't it? Worked for years, and in the end, the solution is not there. What is happening? Why the low temperature regime? Well, this method works only on solitons, so you know the low temperature regime actually is pretty easy. You have the potential, but you go low temperature, so essentially you localize where the potential, you should find just a single relative mode as we do before. So you can analytically check it. You can see if this goes to that, it does not. So you can wonder, maybe you need radiation, but as I show you, like the breeder is actually becoming radiation certain limits, so it's not clear if you have to do it or not. I haven't seen, I'll say, rigorous or like a general attempt to include in St. Gautam the radiation as a separate mode. But I anticipated what we're gonna happen after. Adding radiation as an independent mode is not a solution. Okay. Now you can say, oh, whatever we are doing is nonsensical, doesn't work. But come on, the similar approach in the quantum case works, so it cannot be completely wrong. Plus, there's a nice paper by Buller and others from 1986, where they look at Sinch-Gordon, that is, instead of the cosine, you have Koch hyperbolic cosine, where you don't have a solid, you just have radiation, but still you can have all these linear modes and so on, and then it works. What they did is a hell of a computation going in normal modes, like action variable angles, solving thermodynamics there, and the end what they get is a thermodynamics they would get from a kind of Soliton gas, but based on radiation, exactly with this normalization. So we're in an unsatisfactory situation where something works and something doesn't. Yeah. Yeah. Mm-hmm. That is carried over by the inverse scattering transform, if you want. Okay. But again, you can identify these modes, but they're very nonlinear. So essentially what you're missing is the right Jacobian from one coordinate set of coordinate the other one. And that would be a fantastic calculation, but is a nightmare. In the sine God, if I remember correctly, they managed to find the action angle variable from other means, not really inverse scattering, and find a set of modes that behave like the radiation that I showed you before, but it is nonlinear. How do you do that from the fields? That's the point. And also when I change the variable for getting radiation, I cannot just do it on the field itself, because if I just have the field and don't consider the canonical conjugate momentum, I don't have really a canonical transformation between the field and the A modes I wrote before. So it's better to not integrate it out, but consider them together, because you can play with canonical transformation. Okay? But of course, in spirit, I could just integrate away the momentum, have the field. The problem is that I do not know what to do with that. Giga? And also, like, I need to speed up a bit. So quick question, please.
And so here, if you integrate out the momenta, you can analyze the partition function as a iteration of some transfer integral. But there, I mean, it's not clear what the integrable structure is. I mean, you can do this for irrespective of integrability. And you need to set the spectrum of that operator, but there it's not clear what the integrability structure is.
So as I have already anticipated, the solution to this story, okay, that makes you to understand conceptually what's going on and allow to fix the problem, even though full classical solution is not within reach yet, is doing the semi-classical limits. What I want maybe to highlight before is that put some like asterisks here. This guy here, this guy here. All these people here tried the semi-classical limit because thermodynamic Bethe was already developed. You see the calculation has something weird at a certain point, and they just didn't interpret correctly what was going on. Okay, so you find all the semi-classical limits in the literature, but the final result is not correct. But not because the method is not correct, but because there were some mistakes in the calculation, but highly non-trivial mistakes. Okay, I'm not like talking down these people. They're super smart, they did a fantastic job, but they missed this important detail. Okay. All right. Now, we are right here. I want to say some words, need to be a bit shorter, but I think it deserves credits and also why they continue working on this and why it works. I want to say something about this line of research now, this part here, okay? So, and for this actually is easier to work, the spirit is the same, okay? But for also historical reason here, instead of St. Gordon, I will work with the nonlinear Schrödinger equation, right? There's some C. C is not really important in the classical case, the magnitude apart from the sign, okay? If the sign is positive, this theory is really the same as Sinch-Gordon. If it is negative, it looks like St. Gordon, but you don't have a topological solitons, but you have, they want to be breeders that are non-topological solitons, okay? But from this and small difference, the story is the same, okay? Now, you can also not consider thermodynamics and just ask the problem. If imagine that I have a soliton is arriving here, and you have other solitons in the game, how will this evolve? Well, after such a long conference, we know the picture. What will happen, like every time it finds another soliton, it scatters somehow, okay? So this is wanna be the bare velocity. This will be a soliton we'll have in the vacuum, but since it's scattered with other guys, it's piling up an effective velocity. The effective velocity depends on the scattering shift. Now, you can write down a thermological way. These are equations that have been discussed by Benjamin, Marcos, and I forgot how many people now. I'm sorry that I cannot quote the whole audience, probably. Let me put this on I to be consistent with my notations before. Notice that the I prime, when I write this, I'm just considering averages, okay? It's just the normalization to the scattering shift. Of course, I have a target soliton that will fill the average of the other solitons. It fills the average, it doesn't fill the fluctuations. It means that I don't need to compute this, the whole thermodynamic machine. I just need to know the average root density that maybe somebody else gave me. I'm not determining it from initial temperature, whatever. Somebody else gave me, and I just plug in to see what happens. Okay. Now, you get a phenomenological way to derive it, but actually, these have been formally or rigorously derived by Gennady L in 2003 for the KDV, and then by him and collaborator in 2005 for the nonlinear Schrödinger. Okay, this is KDV, and this nonlinear Schrödinger. Okay, just notice that have been like 11 years before we got the GHD. Okay, but they did it without a GG, as we're used to think about. Huh? No, that's what is not, well, let's say like this. If you talk about quasi-particles like this, it's much easier to think in terms of solitons. Okay, indeed, all this line of research has been done really on solitons, so attracting nonlinear Schrödinger. And when I talk with them about radiative modes, they've been a bit, how do you include that in thermodynamics or in hydrodynamics? Well, we know how to do it from these semi-classical limits, and there's all the literature doing here. But usually, these people do not focus on that. I really wrote them as separate lines because they don't talk much, okay? Because it's this, like how do you build the root density? They have a way to detect it based on inverse scattering that is kind of easier if you have the solitons. You can also put the radiation, but for them, this is kind of an open problem, I would say. Yeah, so maybe I say something imprecise, or maybe. Yeah, please go ahead. In the meantime, I just write.
So the way that they derive these things is not really by starting with the multi-soliton solution, by starting with so-called finite gap solutions, which correspond to periodic boundary conditions, and taking appropriate thermodynamic limits, and then interpreting the result as composed of solitons. So it's a bit subtle. So they don't really have the kind of exact soliton gas picture yet.
So if I can add my part of the story to that, indeed, you're going to see later that boundary conditions are important to solve the thermodynamics. Okay, boundary conditions are really changing the contour of the theory, that you can interpret as solitons only in the infinite line problem, but not in the finite case. And they're like working, as Benjamin said, in inverse scattering with the modulation theory. They managed to rigorously find this, and later the modes that were considered interpret as a gas of solitons. If I'm not mistaken, it's easier in that case to work with a discrete spectrum rather than a continuum, in technical terminology. And the continuum one will be the radiation. This I hope that I managed, but you're going to see in a minute. Okay, and so for them is technically difficult. It turns out in the end of the story, from what we understand, they should not really matter. Okay, so there are no fluctuations here. How you do determine this guy here? There's a beautiful chapter of mathematical physics that actually Herbert already introduced us next the previous week. I just want for this I, you have different solitons, different amplitude. So it's just the index labeled the soliton. I can use sigma as a continuous parameter as before, and we run from 0 up to infinity. Your solitons infinitesimal size up to infinite size. It's the height of the soliton if you want, okay? Say it again. You have two parameters for the soliton. One is giving how fast it's moving in space, and the other one is his height, and it's conserved. No, attractive. I don't have dark solitons. The solitons here belongs to the attractive case. They're bright solitons. In the repulsive case, in principle, you could have repulsive, you can have dark solitons, but it turns out that if you want to do thermodynamics or hydrodynamics, you can write the full things on in terms of relative modes. You can understand from this phenomenological picture it works, but actually connects to one of the papers that I just erased. When they do it for Sinch-Gordon, you can do the same for the nonlinear Schrödinger. So that is safe. Okay. How do you get rho I without StatMech? Well, you can do, it's a full mathematical topic. It's called inverse scattering, inverse or direct scattering. Okay, we just mentioned inverse scattering for meaning the whole business. Okay. And here are going to be slightly quicker, just because we have already seen it a couple of times. Essentially, you can see the nonlinear Schrödinger as a compatibility condition for an auxiliary linear problem. How does it work? Let me introduce a new field. This is just a field introduced in one dimension, depends on x and time, and this actually would be a two-dimensional vector. This depends on some rapidity and depends on the field nonlinear Schrödinger. This is a 2x2 matrix. And here again the field. Okay, I have this equation, but I have a relative equation with another matrix. Okay, like this. Okay, these are matrices that depends on the field of the linear Schrödinger and on a parameter that is called spectral parameter and is actually related to the rapidity that we introduced before. Okay, for you, this matrix looks like this. We put C star guy here. Okay. Of course, everything is computed at a certain point in space and time. V has another form, it's slightly more complicated, we don't really need it. Okay? Cool. Why do I need all of this? The fact that you can see that, of course, if you have this equation, you should have, you can take the derivative of x of this, the derivative in time of this, and the two equations give you the exact same result. Okay? So the two equations are compatible if and only if the following requirement is satisfied for every auxiliary function. Okay? And this turns out to be true if and only if psi satisfies the nonlinear Schrödinger. Okay? So it's an if and only if. But notice that here we have some free parameter. So in principle, we have a lot of different compatibility conditions depending on the parameter theta. Okay? And we're going to use like this to generate the concept charges of the model. I will just define the transfer matrix as the ordered path integral in terms of the U matrix. What I'm doing is simply I'm solving formally the. Sorry, I really think that I mess up the notation. It should be x, it should be t. Sorry for this. I'm formally solving this equation. Okay, I can write formally as a random path integral. But now, if this compatibility condition is satisfied, okay, and you want to consider, and this is where boundary conditions are important, not parallel boundary condition, but what is called whole line condition, that you have the field that is running non-zero only in a finite interval and then goes to zero, and I choose these two intervals to be larger. Okay, if you do that, you have a compatibility condition. You can check that the trace of the actually this specifically holds also for the periodic boundary condition, but I'm going to need this problem in a second. You can check that the time derivative of the trace of the transfer matrix is 0. Okay, and the transfer matrix depends on scattering parameters. So this, if you want, is generating conserved quantities. The problem is that you need to work a bit to make them local to use in thermodynamics, but this is a good generator. The trace is a bit difficult to handle with. So what people usually do is to look now at the whole line problem, and the whole line problem defines a slightly different transfer matrix. That is nothing else that the same object, but where I take care of some residual oscillating behavior. Like, let me put like this is from y to from x to y, and this will be the limit of this guy minus x. This extra term is just to ensure that the transfer matrix is going to a finite value at large space and is not keep on oscillating. And this, you can parameterize it as the following. And what is non-trivial, that in this case, not only the trace of the guy is conserved, but this single guy here is conserved in time. This is, if you want, a wannabe conserved quantity, still is not local, not necessary at least, okay? If you want to do local charges, you should do a bit better. And this, yeah?
I think I missed. What is P in the transfer matrix?
It's just a parameter. Like you can, by symmetry, you can parameterize like that. Okay. But I'm calling A only the first entry. B is the second entry, just a definition. But because of symmetry, it has like that, you can just parameterize them to two quantities.
Inside the T tilde?
Sorry, Pauli matrices, sigma Z. So I should have said like that 2 by 2 matrix, so I can use Pauli matrix like a proper basis. Okay. So we are running a bit short here. So I will just say that if you do a Laurent expansion of this guy here, so theta is very large, okay, you can show that what you get are all the local conservation law. These are local conserved quantities. Okay, and by doing analytical studies of A, you're going to find that it can have zeros in the complex plane. Okay, so A can be written in the on complex analysis, you can write the logarithm of A. These are just standard Kramers-Kronig dualities. Dualities. It's not really needed, yes. Where I parameterizing this guy has the pole in the complex plane. And what you find out is that if you look at the charges, you're going to get that this guy here you can interpret as solitons. If I look at the charge, you get here a summation over poles with some energy in front of that or other charges, exactly the charge of the solitons. But plus, you're going to get an integral from this, okay, that is suggesting some radiative mode. These are solitons. And this is the whole problem in the from the inverse scattering, that if you look at that, it seems that we have both radiation and soliton. But this is something that works for infinite line problems, so the boundary conditions are going to 0. But if you want to do thermodynamics, instead you need to consider the periodic boundary condition. And this complicates the story. You hope they can use in the thermodynamic limit the same modes, but this is not necessarily true. And this is where the problem, the Soliton gas picture comes in. Okay? And people working on Soliton gases essentially are either analytically or numerically solving that equation to determine the density of the solitons to plug in their kinetic equation. But they're not solving direct thermodynamics. Okay. And this is connected to some questions I received before. In principle, if you could do the whole business, not only infinite line, but periodic boundary condition, and sum over the analytic and analytic part of A, you would be able to recover the partition function. But this is a tremendous difficult problem. Okay? People have not done it. They did something for the kinetic picture, as Benjamin was saying before, but not for thermodynamics itself. It's more difficult. Okay? But still, if you want to look at fluctuation, we should be able to do thermodynamics, and this is an open problem. And now, I'm going to go to the last part of the story, that is this line here. I'm going to tell you the ideas, maybe skip some of the nasty calculations, but you're going to see. Okay, so on the classical case, at the moment we have that the StatMech is an open problem, and we have the kinetic picture. On the quantum case, we have that the statistical mechanics is solved by TBR. Let me say that this is correct. And we have also GHD. GHD is, if you want, kinetic picture plus thermodynamic data. So it has a bit more than just a kinetic picture. Okay. The idea now is to use the information of the quantum system to get information of the classical system. Here, everything is well-defined. We take the limit, we should end up with a well-defined solution. Okay? Example. We can have the Libriniger model that we have seen in many talks, like in the one of Marcus, for example, it was the main character, definitely. That is defined like this, where I'm stressing that these fields are quantum bosonic fields. This is quantum mechanics. This is some interaction that is quantum. But there is another model, this is the nonlinear Schrödinger, that looks exactly the same, but instead of having quantum fields, it just has classical fields. Clearly, the two guys are not too far from each other. One is the quantum version of the other. Indeed, you can check that in proper semi-classical limit, dynamics, thermodynamics, and so on of this has to go to this. And this you can check without using integrability. But now we have also integrability. We can use the whole machinery to solve the Soliton gas problem here, Soliton gas statistical mechanics here, avoiding the jump in making some answers that previous literature did. Okay. So I already put there the references. Here I will follow directly what we did with Rebecca in and JS in 2022. There have been other development. Part of the story actually is not completely written here. We found out later in a paper with Giga DNA in 2024 on the Landau-Lifshitz. Okay, but I will tell the whole story together. The idea is doing semi-classical limits. How do you understand it? Well, let me start from the pre-case, that is the simplest one. If you do thermodynamics, you're going to get in the quantum case Bose-Einstein distribution. Okay, beta and mu. And you can check that if I go to the high temperature regime, that means beta goes to 0, what you're going to get for the mode distribution is just religions. You expand the exponential, you get this. Okay, this is pretty trivial, no? But this is exactly the equation of relative modes. Indeed, if you don't have interaction, we know that the nonlinear showing just relative modes, a single relative mode, we can solve it. But now we can do the same job using the finite interaction case. There's an important part in thermodynamics or integral mode, that is the entropy is known. And it has always the form connected to Vincenzo's question of a Fermi-Dirac distribution. Okay, so this was a problem in the classical Soliton gas because it was an ansatz. Here we know what it is. Okay. The semi-classical limit is achieved in a simultaneous limit of high temperature, as we see. That means large mode occupation. But of course, if it is large mode occupation, you're going to have like this guy here will scale like the density, but this guy here will try to scale like the density square. To make them to scale simultaneously at the same speed, you have to normalize the quantum coupling. Okay? So you can do the whole things. If you have that the charges in the quantum case, they're scaling like, let me set a h bar parameter to make the limit, classical, and together the quantum interaction instead going small, classical interaction. And here I need to take H goes to 0. Okay, and then it's up to you to understand these modes, how they are go into the classical modes, to build the entropy and so on. Okay, in the quantum linear model, here in the attractive phase, that is the most interesting, you still have solitons, but those are quantized. You have a quantized version of the solitons. The energy is slightly different, but the semi-classical limit goes to the energy of the classical soliton. And the same for the scattering shift. All this stuff is tabulated. You can just crank the machine and start mapping one-to-one all the things. These are some calculations that I will unfortunately skip from the interest of time, but I will highlight what's happening. You can take the entropy, the total entropy of the gas, okay? Try to write it in terms of the solitons, the nonlinear Schrodinger, okay? Here there will be a summation over the internal index. I'm gonna go to sigma because this is how I wrote in the paper, is the internal index I that I will do at some point, okay? And if you do naive the computation, you're gonna find this. And this we like because it's soliton-like contribution, soliton gases, but plus there is a bloody term that looks like this, H bar. If you do a naive limit from the level of the entropy, you find the residual H bar into the game. That of course is nonsensical. You should find a well-defined classical model. What's going on here? This is a singularity. This is not a chemical potential. It would be a chemical potential if I put a sigma here, but it's not there. This is not a chemical potential. And the fact is that there is a singularity here, but there is also a singularity hidden in the integral coming from the large extended solitons. Okay, sigma small means the solitons are large. And this is connected with the problem of boundary conditions. Imagine I do a fine size, okay, L. If I have a soliton that is very well localized, I can put into the game. But if I start having a soliton that looks like this, maybe it's not very high, but it's very wide, I need to exclude it from the counting. Okay? Now, these models, these are not too many, of course, because you could imagine that if the size is larger, then I have less soliton that exceed the size. But on the other hand, all the charges brought by these solitons, for example, the energy of this guy, of the solitons, looks like this. Sigma 3. This guy is going to 0 when sigma is small. And this works for all the charges. So when you do thermodynamics, we have that these modes do not weight much from the point of view of stat mech. You can put a lot of them, but they should be excluded from the volume. Okay? So essentially, you have that doing the infinite volume limit and the semi-classical limit, they do not commute. This is correct what we are doing. This is wrong. Because in the quantum case, we can handle safely the boundary condition, periodic or non-periodic is the same. The classical case, you have this problem. Okay? Now, the strategy here is that you can write this equation. You can put a cutoff here that depends on H, because the solitons are quantized. So a soliton cannot be smaller than something. There is an effective cutoff for the quantum soliton that is maybe very large, but there is a cutoff. You solve the thermodynamics with the cutoff, and eventually you do the limit of the TVA equation. You recover the classical equation, you recover from that the classical entropy. I can tell you more later if you're interested. Now I would like just to write it, and since we start 5 minutes later, I would like to show 5 minutes of slides, if it is fine for you. Otherwise, we can also close it here. Maybe we can start having the slides. In the meantime, I write this. So if you look at the entropy, this will look like some solitons This is what you expect from standard solitons. But then, and this is a bit unearned in turbo systems, you have extra terms that depend directly on the index of the soliton. They don't depend on the fact that you are soliton or not, but depends really on the amplitude of the solitons. This entropy, we managed to get it only from all this machinery. It extends to other systems, Saint-Gobain, Landau-Lifshitz, and so on. It is an open problem to derive in the purely classical case, but this fixes thermodynamics. You can check the computation that has been done previously by the people that didn't manage to, like the checks have been done here on the failure soliton gases. If you do thermodynamics with that, this matches in all the possible limits, and also you can run numerics. I just have a couple of slides because I want to finish the story, but I will be super quick, okay? Right. Well, it's not working, so I'm going to stay here. This is just extension, sorry, to experiment on the whole line, because we discussed theory, but the same one-to-one corresponding quantum cluster can be done also at the level of experiment. Okay. And I want just to play a bit with the timeline. Is the same plotted picture I did before, but for experiments. Well, the quantum line is as follows. We have like a very nice review from yesterday by Marcos, who told us that in 2006, they started developing simulation, quantum simulators in optical lattices of thermodynamics, Thom's gas. Very nice experiment later in 2006 by Kinoshita et al. Doing non-equilibrium dynamics. Later, 2014 is first probe of generalized Gibbs ensemble called atoms. We have the GHD paper 2019, the first. Rapidity measure in 2020, and all other experiments. But similar things can be done also in the classical level. And it's really fun that is kind of toe-to-toe in terms of time. First kind of the analogs of classical quench, so non-equilibrium physics done in photonics, talking about 2006. 2014, they start studying integrable turbulence, that is how soliton gas people call GGE, and is really the same year. But they don't have the theoretical method to fully understand it, but they're studying experimentally. 2019, dense soliton gas, that is the same as generalized hydrodynamics, with the same years. Guess what? 2020, they measured the rapidities in the classical setup. Again, same year. Well, of course, there have been other developments. I just want to quickly show two things that we are doing now, just because we are really matching the quantum and classical worlds. Okay? Experiments in the classical case are done with photonics. Essentially, there's an optical fiber. You inject an electric field. It's a nonlinear medium that is described by the nonlinear Schrödinger equation. Okay? The nonlinearity in the equation comes from the fact that the medium is nonlinear. You can do what in the quantum case we call a quench. We put some initial condition, let it run, and see what it happens. Okay? The fact that these experiments are super precise, and of course they're classical, but on the other side, you can really pinpoint in real space and times where the excitations are. Okay? You can see beautiful picture of solitons where you clearly see the measurements of the effective velocity. It is something at the moment in the quantum case like this is a bit difficult to do. We have also the concept of GG. For them, it's integrable turbulence, but now we know how to solve it. We did a very nice experiment in the repulsive case when we can really measure the rapidity distribution. This is a single additive mode. You should see two plots, red and blue, focusing on the initial and final condition. And it is very well conserved. This is an very nice, high quality experiment on integrable physics with very small corrections. Other observables instead will relax, of course, because at the beginning you have some state. These are just random plane waves, and the nonlinearity kicks in. You can see the relaxation observables. And here we are looking at the distribution of the fluctuation, the local density of the field. These are some exact calculations that we can get through semi-classical limits. Now we can use it to interpret experiments. Something that I really like is that in the classical case, measurements are not destructive. The quantum case, once you measure the system, you destroy it. In the classical case, instead, it is not. You can keep on evolving, and so you can measure correlation functions. We discussed it in previous talks that there are, in turbo system, expect ballistic correlation function with correction diffusion, of course, but the leading point is ballistic, and we have formula in GHD to do that. The kinetic picture, they don't have it because they don't have the statistical GG that instead we have from all this machinery. This we did in the nonlinear Schrödinger attractive side. This experimental measurement, a two-point correlation, the density function, if you want a near Schrödinger. It goes down, but if you scale it as an instant, there is a nice ballistic behavior. And we compare with theory by extracting the density of state, the root density from the experimental data, plug in the whole machinery of thermodynamic better answers and GHD to get a very nice matching with the correlation function. And of course, like this at the moment, I want to explain is still not doable as far as I know, but we can do it classically. We can start now studying about diffusive correction, unconventional fluctuations, and so on. I want to conclude because I'm taking a bit over time. So today I really want to make a strong connection between the quantum and classical world or in turbo models, passing from thermodynamics and hydrodynamics all the way to StatMech of Soliton gases and the kinetic picture. This connection is theoretical, but also you can do a parallelism at the level of either numerical checks. The quantum case are very difficult, while in the classical case, we can just run a Monte Carlo approach that is quite easy. And we can also have a correspondence with different experiments, okay? This leaves out some important questions. On the theoretical side, something that is, I think, is fundamental problem is how to understand Soliton gases StatMech from purely classical cases, but we do not have at the moment an idea. On the practical side, we can keep on using techniques of the quantum case to the classical case and maybe the other way around. There are beautiful pieces of mathematics in the classical case that maybe can be converted to better understand quantum case. Experiments, both worlds can benefit from the expertise of one and the other one. But this also leaves out a big important question, what is really quantum at a large scale? Because if dynamics and experiment just depend on the fact that we have some conservation laws and symmetries, how we can really be sure that we are looking at something that has quantum nature in the system? This is a big important question that we discussed during the workshop. I'm really concluding, apart from two announcements. There are two upcoming conferences in Paris that I'm co-organizing. One is a better like well-defined stage than the other, but we are almost there. We're gonna deepen the connection between integrability at the physical side, the mathematical side. Okay, if you're interested, that is the QR code. Another conference is just the same week. So if you're in Paris, quite to be exciting time to be there. It's gonna be more focused on quantum aspects of not only integrability, but in general. We're gonna plan to have like a threefold connection between analytics, numerics, and experiment in non-equilibrium quantum systems. So not only GHD, but also maybe a bit of that. Last thing, and then I'm gonna like stop it. I'm supposed to start hiring PhD and postdocs this fall. The announcement is not out yet, but I would be really grateful if you can propagate information to interesting candidates. I'm very happy to start chatting with them. With this, I'm really over time. Sorry for taking your time, and thank you very much.
Thank you, Alvise, for this wonderful lecture.
I hope you had fun.
Sure. We could have some very quick questions. We had lots of questions.
So I have one question about this limit of quantum to classical. So in the classical case, I mean, if I look at the delta Bose gas attractive, I mean, you have bound states.
Yep.
Do the bound states converge to the classical solitons?
Yes. Yes, I say it very quickly. I maybe understood that I should have been planned better, like at the end part of the lecture. But yes, in the attractive case, you can check that the quantum bound states are going to the bright solitons. Indeed, this is the energy of classical bright soliton. In the quantum case, you have something similar. The index, this is discrete now. And the energy now this will be the classical. This is the quantum interaction. And it's like this. Now, you get the bright soliton in the limit where the bound set is large. So J should be larger. And if J is large, you don't recognize if you have J or J minus 1. So this becomes J cube, that is essentially sigma. You can really do it at the level of energy, all the charges. You can really prove it. And also at the level of the scattering shift between the various solitons. So they really are one-to-one correspondence.
Can you comment on the repulsive case? Because you say that the attractive case, everything is dominated by solitons.
Yeah.
In the repulsive case, I would say it's quite the opposite.
Indeed, like the repulsive case, I think it is quite interesting, but it's a bit more easy from this point of view, okay? In the sense that eventually what you get in terms of the entropy is exactly what you would expect, but it's not based on solitons, but it's based on radiation. In the repulsive case, if you want a repulsive case, is closer to the non-interacting point than attractive, because you just have some radiation that get dressed by the interactions. You have only a single radiative mode. So the situation, let me just repeat it, in the nonlinear Schrödinger is, on the repulsive case, a single radiative mode. On the attractive case, on the thermodynamics, this gives only solitons with renormalized statistics. The inverse scatter will suggest solitons and some kind of radiation. But how this picture works is that the radiation is discovered as a limit of the solitons. There are situations where both radiation and soliton can coexist together. For example, this happens in the Landau-Lifshitz equation at the axial anisotropy. There you have some solitons that describe in a certain limit a branch of radiation, but another branch of radiation that is on its own mode, also with renormalized statistics. So there is a very complicated zoology. We know how to do quantum to classical, but we don't have a general understanding of what we should expect here. Okay. Please. Yeah.
So again, perhaps I'm referring to the quantum theory only now, but I would like to know how this is done in the classical theory. So in the quantum theory, a lot is known of how to avoid the overcounting between the solitonic modes and the what you're calling the radiation modes. I mean, when you are in the one soliton sector, so when you are doing the normal mode expansion of the radiation modes, you have to take out the degrees of freedom corresponding to the soliton. So this is collective field formalism of Tombulis and Sakita and so on in the 70s and also in the 80s. And and when you have more and more solitons, you have to keep subtracting out more and more from the radiation modes. And eventually, when you do this duality between Sine-Gordon and the Turing model, the duality is exact. So, so I wonder, what is possible?
The fact that at the level of thermodynamics of quantum particles, okay, quantum field theories as well, okay, you can have the quantum Sine-Gordon, that is a field theory, you don't have the physical particles, okay? But once you identify the modes are always of fermionic nature, okay? And this is like, is coming from the beta equations, okay? For really a solution, the macroscopic beta equations is something that you are lucky in the classical case, okay? That allows you to fully characterize all the solutions and to understand, because they obey a Pauli principal exclusion that is engraved in the beta equations, that the statistic must be fermionic. So you don't have a distinction there between soliton or radiation. You just have some modes that behave like a fermionic, that in the proper classical limit, they can be identified as the topological soliton or non-topological solitons or other modes, okay? This you can check at the single level solution, at the level of single solution. And in this way, we did it the full limit at the level of thermodynamics. Okay, but this is something that is taken care automatically from the quantum case. You don't have the phenomenology of soliton gas is well established. And of course, what you can do is, let me start from the classical solution, try to quantize it. There are ways to quantize the soliton radiation top on that, but this method is approximate and doesn't know about integrability. So that is a closer connection, but it doesn't use integrability. So you cannot go exact.
Thank you. Thanks a lot.
Considering the time, let's defer all the questions for the tea break. And we come back at, let's say, 12:05.
Happy to chat more if you want.
Yeah, wonderful.
Very over time, but I want to finish.